I'm going to talk about how mappings relate to the idea of linear approximations. And this really unifies everything we've been doing with derivatives, since you even learned them, because derivatives really are a mechanism for getting a linear approximation. And I want to do a couple of examples first. One is a curve. Let's say the curve is a familiar one. Let's say x of t is cosine t sine t. And that parameterizes the circle. And I want to discuss the tangent line. Let's say, to be specific, let's say t naught is pi over 4. And I want to talk about the tangent line as the linear approximation to this function. That this is a curve that goes around in a curved path, but this straight line is also, we can describe that as a parametrized curve that goes in a straight path, and near where they touch, they're almost the same. If I blew these up with a very huge magnification, they would start to look more and more and more like the same until they were indistinguishable. And that's what we're familiar with the tangent line to a curve in BC calculus. So let's look at how that worked. We took the velocity vector, which is just the derivative, and that's the derivative in this new sense. Oh, let me go ahead and try and adapt to this new convention, though. Because these are two outputs and one input, I'm going to draw it right as a column vector. And that makes sense, because we're going to get an arrow out of this that really makes sense to think of as a column vector. Okay? And so we're going to take v at pi over 4, or x prime of pi over 4, is minus 1 over root 2, 1 over root 2. And that's this arrow going up here. Now, that's the derivative as a vector. Oh, that needs a vector symbol. But what we really often need is really a function that derivative gives us the key to, namely a new function of t, a new parameterized curve, whose velocity vector is the same and is a straight line. And so we know how to do that. We have the point, which is x of pi over 4 is equal to 1 over root 2, 1 over root 2. And we have the vector v of pi over 4. Just recopy it from what we did. And we know how to get the equation of a line from that. Now I'm going to do something slightly different from what we were doing before. What we were doing before, forget the tangent line, is we sort of forgot this original t variable, and we used a new t variable for that tangent line that started with t equals 0 here. That's not really a great idea, actually, for a lot of things, because if we're trying to have this particle following the curve trajectory and a new particle of our own invention at the same place and at the same time going in the same direction, then, well, the key thing we need is at the same time. And that's not going to work if this guy gets there at t equals 0 and this guy gets there at t naught equals pi over 4. So it's easy to fix. What we're going to do is we're just going to take our point plus the vector, and I'm not going to multiply it by t. I'm going to multiply it by t minus t naught. And so that's going to be our linear approximation as a function of t. And so if we write it out explicitly, you know, I'm going to take a common factor of 1 over root 2 out of everything. And then I just get 1 minus, and t naught is pi over 4 here. And then 1 plus t minus pi over 4. And that's the vector. Okay. So in general, L of t is going to be x of t naught plus x prime of t naught times t minus t naught. That should look, ooh, there's a prime there, that's very important. This should look pretty familiar. This is just like f of t naught plus f prime of t naught, t minus t naught. That's the BC version. We usually use x there, but it doesn't matter. Okay, so it's exactly that tangent line approximation. And so what we've got is the value plus the derivative acting as something that multiplies something else, multiplies an input, and gives me a linear kind of gadget. Okay, so that's how the tangent line works as a linear approximation. Now let's do another example. Let's do a graph, a surface, which is a graph of z equals f of x, y. Let's say, to be simple again, x squared plus y squared. And let's say at, let's see, just to be interesting, let's say 2, 3. That's my x naught, y naught. And I'm using x naught, y naught, t naught to really emphasize that there's a fixed value of t that determines where we're doing this. And then there's a variable that goes into the linear approximation, which says, well, what if we walk away from that? What if we change t a little bit away from t naught? How does this curve change, at least to a linear approximation? Okay, so we know that looks like a bowl. And I'm going 2 units in this direction, 3 units in this direction. And I'm getting the tangent plane to that thing. Okay, so this is something we've done already as well, that the tangent plane is given not by z equals x squared plus y squared, but z equals z naught, which is just f of x naught, y naught, but I'll just abbreviate it as z naught for right now, plus the partial derivative fx evaluated at the point in question times x minus x naught plus fy at the point in question times y minus y naught. And now here's where this putting things in matrices is really handy. And this is something that our main text observes, and that the handouts didn't really observe very well, is that this is really, you can think of this as the dot product of the gradient with a vector. So we can think of this as z equals z naught plus the gradient of f evaluated at that point, dotted with the vector. It's really a vector difference. Oops, no, I don't need a vector over that. Sorry, there's no vector there. So you take the vector x. Now here's where the vector x comes in. I'm going to make that into a vector. That's a dot product. And then x minus x naught. So I'm making everything into a vector. I take the vector position x. Here's the x naught vector. And then I walk away from it a little bit to x. Oh, not x. Shoot, it's hard to erase here. That's just x. And I try to figure out how are these heights different. And I'm settling for a linear approximation, that I walk off not on the curved surface, but on the tangent plane. And you look at the vector difference between the point you're really interested in your base point. You dot that with the gradient, and then you add it to the height you already had. Very similar to what we had before. So notice the similarity here, and I'll do the explicit example in a second. The base value of the function, f of t naught or z naught, times derivative of a certain sort times a change in the input. So derivative dotted here with change in the input plus z naught. Well, there's an even better way to say that, which is we now know that the gradient of f, x naught, y naught, that really is a row vector. And and whenever we see a dot product, we should suspect, maybe one of those actually deserves to be a row vector, and it's really matrix multiplication. So that's really a row vector made out of these two numbers, df dx and df dy. And so my equation for the tangent plane approximation is now the base point value plus this row vector just times the x minus x naught column vector. Okay, and so that would have coordinates x minus x naught, y minus y naught. It's just another way to write the dot product, but it fits better with the matrix version of things. So in our example, real quick, we're going to have z naught is f of x naught, y naught is 4 plus 9 is 13. Fx at 2, 3 is 2x, so that's 4. Fy at 2, 3 is 9, and so we're going to get z equals 13 plus 4, 9 Gotta stop.